Hello and welcome to the Earth Science Associates video on the tieback tool. This is a part of the GOM³ Analytics Add-on and can be accessed through the GOM Smart website. This will be a deeper dive into the tieback tool, so if you'd like just a briefer overview of how the tool works and how to get the results, check out the link in the description below. The tieback tool utilizes the bathymetry to find an optimal path from a given origin and destination. Now this optimal path is a balance between distance and slope. Since the seafloor has mountains and valleys, if you were to encounter a mountain, the question would become, do I go up and over the mountain or do I go around the mountain? And that would of course depend upon the distance you'd have to travel to go around it, and then the slope you'd have to do to go up it. So we know that there is some delicate balance here, and then other people treat distance and slope differently, and so we let the user define how this balance plays out. And we'll go over an example of that. And what does the heavy lifting in this algorithm is Dijkstra's. And Dijkstra is an algorithm used in network theory to find optimal paths, so we utilize it in a very similar fashion. So here's a map. In the bottom you can see KC31, that's going to be our origin in this example, and then at the top A Augur TLP platform, that's going to be our destination. So we have a lot of extra information. We have those leases out there, those aren't going to play a role, so we strip them away. Now you can see a lot of various colored polylines. Those are the seafloor anomalies, so we will keep track of those, and we give you the option to avoid them if you want. But we treat them all the same, so we'll gray them out there. And then we discretize up the bathymetry, and you can see that. And then any one of the cells that have the seafloor anomalies, we've grayed out. Zooming in on our origin, here you can see our cells, and they're actually 100 meters in size. And what's going to be important to keep track of is from any one of the grid cells, you can travel in 8 possible directions. That would be up, down, left, right, and then the 4 different diagonals. And so the green you can see is the up, down, left, and right. And those are both 100 meters in distance. And so then the purple is longer, and using Pythagorean theorem, it's actually 100 root 2, and root 2 is about 1.4, so it's about 40% longer traveling the diagonal direction. That's going to be important to keep track of when we are looking at our algorithm. Now that our grid is laid out, it's time to start calculating the cost, because that's what Dijkstra's algorithm requires. So let's say we are on the star, and we're going to consider different ways of moving to the red square. Well, there are 2 very simple ways of doing that. One would be the purple option, that would be traveling northeast and then northwest to get you there, and then the green option would be traveling north twice. So we lay out our values from our bathymetry, and then using these values and then the distances, we will calculate our cost. The exact function we use to calculate the cost, we will keep proprietary though. So in the purple option, I calculate a cost of 1.4, and then a cost of 6.6, and that gives me a total of 8. And the green option, 7 and 2, for a total cost of 9. So we can see that in option 1, the total distance is longer, but the slope is less severe. So this increased distance adds to the cost, but overall with the default settings, option 1 ends up being less costly. So like I said earlier, we do give you the option of adjusting the slope importance factor. At the default settings though, in this example, option 1 was less costly, and so that would be the path we would choose to take. If you take this slider bar and move it to the right, you are saying, I want to increase the importance of slope, and then therefore decreasing the importance of distance. So the extra distance you traveling in the purple option becomes even less of a hindrance to you, and you choose that even more because it costs now even less, especially compared to option 2. If we move it to the left, we're saying now we care more about distance than slope, and so I am less willing to travel out of my way to avoid high slopes. And you can actually in this case see that it changes your path to option 2. So just note that the lower you make the slope importance factor, the closer to a straight line between your origin and ending point your path will become. So after we've done that, for every single cell, for all adjacent cells, right, that was one step basically, or 2 steps to get to the red path. We do this for all of the ways, all the way up until your destination. And then we transform that data into a network graph of nodes and edges. And this transform into a network graph because that's again what Dijkstra's algorithm works on. Now we do give you the option of allowing a maximum slope if there's some slope you never ever want to cross over. we let you select that, and so if there are edges that cross that threshold, we remove them from our network, and so they're impossible to reverse and will never be returned in the output. Additionally, some of the nodes can end up in no-go zones, and that would be things that are near platforms. We don't want your pipeline path going too close to a platform, so we allow that. And additionally, if you select water bottom anomalies, we'll also remove those nodes. Finally, we can apply Dijkstra's algorithm, and it will loop through and go through all possible combinations in a very nice, fast, optimized way, and it'll find the least cost path for us. We take this completed path, we can now see how it works on our grid cells, and of course we transform that into a nice shapefile so you can see it on a map. Here is the interface, which we'll focus on more in the overview video, but for this video we'll go over a couple of the more interesting values. The first being the estimated open oil capacity, and same for gas. And what this tells you is how much, and to get just an estimate, how much available capacity there is. We estimate this based on the difference between the current production and the maximum production. So using this method, there could be more open capacity than we display, but there almost certainly isn't less. The next interesting column would be the average annual oil decline over the next 5 years, and again likewise for gas. And so what this tells you is annually how much extra capacity we expect to be available on this platform. So you can get a quick idea if the wells are starting to die off or if they're really just barely on production. And this value is calculated based on decline curve analysis on the producing wells. So we'll have a nice picture coming up soon in the results so we can take a look at how that works. The results page, most of it isn't too complicated. Most of the information that you typed in, your origin, destination, things like that. This plot is water depth versus distance. And so it's a nice, easy way to see a profile of your slope and how it's changing. These are the cumulative distribution plots, and they give you an idea of how your tieback compares to the other pipelines in the Gulf of Mexico. So for instance, here this is length, and the red line is where this current example lines up. And so it's a little over 60 miles. And you can see that hits the cumulative distribution plot up here, which appears to be about the 95th percentile. So what that's saying is only 5% of the pipelines in the Gulf of Mexico are longer than the current one we're proposing. So definitely on the very long side. However, for the average slope, we're here at about 1%, which is about the 30th percentile. So the average slope of this pipeline would not be very steep, though. And then you can interpret the other ones the same way, maximum slope, the variance of the slope. Here is a plot of the production of the platform. If you selected a platform, we'll give you this. The black dots would then be the current production rate in barrels per day of all the wells that are currently producing. So the ones that are dead, those aren't considered here. And then the green, you can see, is our forecast. And then the brown will be our confidence intervals. And this is actually a very nice forecast, so those confidence intervals are nice and tight. And then you can see a table of the same values here, and you can see how the production is declining. And we, of course, repeat this for the gas, so you can get an idea of that as well. This concludes the video on the tieback tool. We hope this tool is very useful to you, and thank you for watching.